So hi everyone, welcome to the Space Science webinar series. Today's speaker is our very own Ambrish Pandey. He's a postdoc at our center. He got his PhD from IIT Kanpur, Indian Institute of Technology in physics in 2016. Then he moved to Germany at Ilmenau University of Technology, where he worked with Jörg Schumacher. And since December 2019, just before the pandemic started, he joined our center. So welcome, Ambrish. It is all yours.
Yeah, so thanks, Dimitra. I hope you can hear me well.
Yeah.
So thank you, Dimitra, for your kind introduction. So hello, everyone. I'm going to talk about thermal convection in extended domains with emphasis on Low-Prandtl-number regime. So this is the regime which is relevant to the convection in the sun and stellar interiors. So before I move on, I would like to thank my collaborators, Professor Srinivasan, Professor Jörg Schumacher, and Professor Janet Scheel. So most of the work have been done with these people. So the motivation for our work comes from the convection phenomena observed in nature. For instance, solar convection. So if you look at look at the sun, you observe this kind of pattern. So this pattern is known as granulation pattern, granulation network. And as you probably all know that heat generated in the central region of sun is transported towards the surface. And in the outer 30% radius, this transport happens due to thermal convection. So and this is the pattern observed at the surface. And this consists of smaller granules and with typical size roughly 1000 kilometers. And if you focus on a specific granule, then you see that the central region of the granule, bright region, corresponds to hot plasma moving towards the surface, rising plasma. And the intergranular lanes, these dark regions, they represent they correspond to the region corresponding to cold plasma sinking towards the bottom. So I showed two relevant parameters for the convection in sun. These parameters are the Rayleigh and Prandtl numbers. So Rayleigh number is defined as the ratio of the driving force due to buoyancy to the dissipative forces due to viscosity and thermal diffusivity of the fluid. So if you, for instance, if you take water and start heating it from bottom and cool it from top, then convection starts after some critical temperature gradient is reached in your system. And the corresponding Rayleigh number is roughly 10 to 4 in for convection in water, for instance. So you can see that Rayleigh number is 10 to 22 in solar convection zone. So you can imagine how strong the driving force compared to dissipative forces in the particular flow. So this strong driving causes the turbulence to be very vigorous. So we have very highly turbulent flow here. Another parameter is the Prandtl number, which is the ratio of the kinematic viscosity to the thermal diffusivity of the fluid. So it basically specifies the time scales of the momentum and heat diffusion processes. So if you take a fluid and put certain amount of heat and certain amount of momentum, then they both diffuse. And the ratio of these two time scale, so heat diffusion time scale to the momentum diffusion time scale, is the Prandtl number basically. So for very low Prandtl number fluid, here Prandtl number is order of 10 to minus 6. Heat diffuses very quickly compared to momentum. So you have, as I will be showing to you, that the structures in heat are very coarse. Heat diffuses very quickly compared to momentum structures. So the main point I want to make is that despite the extreme parameters and highly vigorous turbulence, highly turbulent flow, we observe a kind of pattern here, regular pattern. And this pattern is reminiscent of the pattern observed near the onset of convection. So when convection just starts in water, for instance, we get a regular hexagonal regular pattern. And we would like to then understand, or we'd like to see whether the regular pattern displayed here as granulation pattern can be observed in Rayleigh-Bénard convection in turbulent regime. And it has been observed in thermal convection that as you increase the Rayleigh number or driving force, then fluid gets more and more turbulent, and any pattern which is visible gets blurred, like you cannot see a pattern. So we try to understand these patterns in a uh, simple setup known as Rayleigh-Bénard convection. Uh, uh, for our study, we ignore certain complexities which are present in solar convection. For instance, flow in the solar convection is also affected by other factors such as Lorentz force due to presence of magnetic field, Coriolis forces due to presence of rotation. Then we have varying, like strongly varying density, temperature, pressure, and that correspond to strongly varying molecular diffusivity and viscosity. So we somehow we come up with a model where we neglect these complexities, and we just consider it a flow driven by thermal convection. So this is kind of an idealized setup, which helps us to understand the flows in like solar convection zone or stellar interiors in a simpler way. So I want to emphasize the importance of Low-Prandtl-number convection, as the stellar and solar interior are almost always occurred by very low Prandtl-number regime. So what is difference? What is the difference between low and high Prandtl-number convection? So for instance, if we take a cylinder and fill it with air and heat from bottom and cool from top, and we find a certain kind of convection pattern at a given driving force. So if we see a convection pattern in air in the cylinder, so if we are focusing here on a vertical cross section of the cylinder, we can see that hot plumes, these hot plumes rise and cold plumes sink towards the bottom. We can also do this experiment with liquid mercury, and we again get similar kind of rising plumes and sinking cold plumes. But we can immediately see that due to large thermal diffusivity of the low Prandtl-number fluid, the thermal structures are very coarse compared to thermal structures in the air. So small Prandtl-number or low Prandtl-number fluid shows coarse thermal structures. On the other hand, if you focus on the velocity structure, so here we show the velocity magnitude in this particular cross section, and we can see that the velocity structures are of similar thickness as the temperature structures. Whereas in the low Prandtl-number case, these velocity structures have much finer, they are much finer compared to thermal structures. So they are very different in thicknesses, and the low Prandtl-number convection, that's therefore is very challenging to study because of very high, very fine structures which we need to resolve in order to study them numerically. These fine structures evolve on faster time scale, so you also need to have very fine time scale in your simulation or in your study to prudently study them. Here is another example from 2D convection. So if you take a 2D flow, you just this is kind of idealized flow, and you this is simple convection flow, and Prandtl number is 12, roughly 12 at the top plate and in the top panel, and 10 to minus 4. So this is towards the solar, towards the parameter in the solar convection. And you can immediately see the structure, the differences in the thermal structure. So here very fine thermal structures, and here very coarse thermal structures are there. So we want to approach this kind of regime in Prandtl number, but as I mentioned, it's challenging. It's very challenging to study a very low Prandtl number regime due to very different flow structures in velocity and temperature field, and very highly turbulent flow. So yeah, so what we get now, so we have basically we have a numerical tool to study turbulent convection. So for our idealized case of convection, we get these kind of governing equations by applying like momentum conservation equation, and then energy conservation, and then mass conservation, and we neglect all the complexities in solar convection. We just have a driving force due to temperature gradient. So this is the kind of equation we have, and we to get the flow structure means to get the velocity field, temperature field, pressure field at all the points in the flow domain, we need to integrate these equations. So we do this by a code spectral element solver called NEC1000, and we simulate, basically we solve these equations using direct numerical simulations. So in this method, we don't require any kind of modeling. We exactly discretize our flow domain and then solve these equations, which gives us velocity, temperature, and pressure field at all the points in our flow domain and at all the times. So we can study the flow structure or whatever quantities we want on the basis of these fields. So the important parameters in our flow are the nonlinear, non-dimensional numbers. These are Rayleigh numbers and Prandtl numbers, as I already mentioned. And for a given geometry and for a given fluid, this Rayleigh number depends on the temperature difference between the top and bottom plates. So for a given fluid, Prandtl number is fixed. We have mu and kappa, which is kinematic viscosity and thermal diffusivity, respectively. They are constant. So we can then simulate these equations and get the flow structure or these quantities. So this is the domain which I'm interested in. So as natural convection or like solar convection or convection in atmosphere, they all occur in horizontally extended domains. And so we study convection in a horizontally extended domain whose width, like horizontal dimension, is 25 times the width of the convection layer. This allows the formation of pattern, a regular pattern, which we observe in, for instance, in solar convection, solar granulation pattern. Till now, like till 2-3 years ago, lots of effort has been put to understand and study turbulent convection in confined domains to achieve larger and larger larger and larger Rayleigh numbers and like highly turbulent flows. And so simulation of convection in these extended domains is costly because you need to put lots of effort in discretizing or in studying these structures, which are, so basically if you take if gamma is defined as the gamma is defined as the like ratio of the it's called aspect ratio. It's ratio of the horizontal to vertical dimensions. Then your numerical or computational resources increase in proportion to gamma square. So they are very challenging. So we solve these equations in the domain of aspect ratio 25. That's what I want to say here. And this is the parameter space I'm exploring. I'm going to explore. So for a given fluid, for instance, whose Prandtl number is 0.7, it corresponds to air. I vary Rayleigh number from moderate values to very high values, 10 to 7, and then I fix a particular driving force, for instance, Rayleigh number, and then vary fluids to see how the patterns evolve and how what kind of patterns we get. And so just to remind you, these are liquid metals corresponding to very low Prandtl numbers. And in solar convection, you are somewhere here at 10 to minus 6. So it's not possible for now to study those parameters from our simulation, but our current results will shed some light on may shed some light on solar convection. So let's see what kind of pattern we get in Mercury. So here we show streamlines of the velocity field. If we look at the convection domain from the bottom region, then this is the pattern formed by streamlines of the velocity field. And this is the pattern formed by temperature field. So bright regions, yellow, bright regions correspond to hot plumes or hot structures moving upward, and dark regions correspond to cold fluid going downwards. And we can see that there is some kind of pattern in the temperature field, but we cannot see, or it's very difficult to see any pattern in the velocity field. And this happens because the velocity field is dominated by the turbulent fluctuations, whereas the temperature field is dominated by mean component. So if we somehow we can remove these turbulent fluctuations, let's see what kind of pattern we get. So we have turbulent fluctuation which evolve on a faster time scale, and if we remove them by time averaging our fields by some sufficient averaging time, then we get this kind of pattern. And we can see that these patterns are very kind of regular pattern observed near the onset of convection. And this corresponds to the pattern in the temperature field. So there is a pattern, but that is hidden due to these strong turbulent fluctuations. So you need to remove these fluctuations in order to get the pattern. And we find that the characteristic length scale of this pattern, which is basically the width of a pair of rolls, this is larger than the height or thickness of the fluid layer, convection layer. So that's why we term these regular patterns as turbulent superstructures, because they are wider than their height. So yeah, so if we do this particular procedure, like coarse graining procedure, to remove the turbulent fluctuations for all our explored cases, then we can see that we find regular patterns for all the explored cases. So for instance, this is the series at Rayleigh number of 10 to 5. So we fix a driving force and we start to change the fluid we are studying. So like liquid sodium, liquid mercury, air, this is water, and this corresponds to some oil, for instance. And we see that regular patterns exist in all the cases. If we fix now the Prandtl number, like we take the case of air and start to drive it at different magnitudes. So forcing is increased continuously from the left to right. Then like turbulent fluctuations are increasing, but we have already removed them. So we can see that the regular pattern also exists here. So the summary is that regular pattern is always there, at least in our explored parameter regime, but we have to we have to get them right by removing the turbulent fluctuations. So another question is, what kind of pattern scale is there? Like, how does it vary with varying Prandtl number or varying Rayleigh number? For instance, if you look at the top panel, I have zoomed it here. Then you can see that the width of the rolls, individual rolls, they vary from one Prandtl number to another. So qualitatively, we can see that they are varying, but we want to quantify this variation. So what can we do to quantify the scale, characteristic scale of these superstructures? So we can take velocity field, for instance, or temperature field in mid plane, and which this corresponds to this kind of pattern. And if we represent, if we compute its power spectrum and azimuthally average it, then we get this kind of thermal variance spectra or kinetic energy spectra, or like based on the vertical velocity. And they peak, like the peak variance or peak kinetic energy is contained in the scales corresponding to the characteristic scales of the superstructure. So we can identify the peak location, wave number corresponding to peak, and then this corresponds to the pattern wavelength. We can also estimate these pattern scales using correlation functions. So if you take velocity or temperature field again in the mid plane, for instance, which is the symmetry plane. Our setup is symmetric with respect to top and bottom. So mid plane is symmetry plane in our case. So we take temperature field in the mid plane. So if you focus on mid plane, then there are hot plumes going upward and cold plumes sinking towards down towards the bottom plate. And if you measure the correlation function of temperature or vertical velocity, you can see that it becomes like it is lowest at the location where upward and downward plumes are occurred. So the minimum location of this correlation function is also they also indicate the pattern scale. So here we computed these pattern scales like for all the cases, and this is the summary of the pattern scale. So for a given Prandtl number, for this corresponds to air. So for instance, in air, if we start to increase the thermal driving by increasing our Rayleigh number, then we can see that the pattern scale is increasing. So this star corresponds to the case of the onset of convection. So when convection just starts, so for driving is sufficient enough to sustain convection, then we see a pattern where the rolls are like the width of the rolls are similar to the height of the convection layer. So if you focus on a particular roll, its cross section is circular. But as you start to increase the driving force, this cross section becomes more and more elliptical. That's what it's indicated here. So for the highest Rayleigh number we have explored, the width of any particular roll is roughly 2.5 times the height of the roll. So aspect ratio of any particular roll is around 2.5. And yeah, so if you look at the temperature at a given Rayleigh number, for instance, you have fixed the driving and you start to vary temperature, you start to vary the fluid, means you are varying the Prandtl number, then you see that this exhibits a certain kind of certain specific behavior. So pattern scale increases if you start to increase your Prandtl number, and then it shows a maximum and then starts to decrease. So this maximum is observed at a Prandtl number of 7 in our case, which corresponds to water. So we always see this kind of behavior. We recently extended our study towards more realistic, more realistic parameters of the for the solar convection. So like we extended our simulations at the Prandtl number of 10 to minus 3. And also at the higher Rayleigh numbers, we see a similar kind of like very similar result, that pattern scale decreases with decreasing Prandtl number. So it will be very interesting to see what kind of pattern scale we get at Prandtl number of 10 to minus 6, which corresponds to solar convection case. And just to remind that lambda is equal to 2 corresponds to pattern scale at the onset of convection. So for a given Rayleigh number, if you start to decrease Prandtl number, you might reach to the case. If we follow this particular trend, then we might go to that particular lambda. Lambda is equal to 2 for very low Prandtl numbers. Yeah, but we have to see that. So now having got these regular patterns, what do we want to do with them? So for instance, we want to see how these superstructures contribute to the total heat transport in our system, how efficient they are or how much they contribute to the total heat transport, for instance, or how they evolve in time. So to do that, we have to get the skeleton of these superstructures, these regular patterns. So for I'm showing here for like regular pattern for a case of Prandtl number 7 at a small Rayleigh number 10 to 5, and we can see a regular pattern. So we want to extract these ridges, which is the basically skeleton of the pattern, And one method to extract these ridges is to just apply some thresholding. For instance, these ridges correspond to very high or very low temperature regions. So if we show only a very high and very low temperature region, we might get some pattern. But this kind of technique works for a relatively lower Rayleigh number. For instance, if you go at higher and higher in Rayleigh numbers, you are increasing your driving force. Then your pattern is dominated by like turbulent fluctuations, like mean pattern. Your turbulent component is dominating slowly. And even if you apply this kind of thresholding, it will be very difficult to get skeleton of the pattern. So to do that, we apply machine learning, like deep learning method, a specific deep learning algorithm, which is known as UNet, to get the skeleton of the pattern. And here is an example. So if we the skeleton of this particular network is shown here, and this is obtained by applying the obtained by feeding this particular input or temperature field into our network, into our UNet network, and we get this kind of output. So just a little bit detail of this UNet. So this is this particular UNet algorithm. It has two branches. This is contraction branch, and this is expansion branch. And within the contraction branch, we have certain in total we have 28 layers in our network. So within each layer, there's certain operation we do. So we feed, for instance, we feed this symmetrized temperature field in mid-plane. So we take temperature field in mid-plane and we symmetrize it, because we are interested in these hot as well as cold ridges, and there are two different types of features for the machine or for the computer. So we make them of one type by symmetrizing this particular temperature field, and we define it like here. So we take temperature field theta, and we then do this kind of we convert them in this. So all the black and like bright and dark ridges, they turn into bright ridges. So we feed this particular image into our network, and we train them. We train our network by just like annotating it manually. So for few snapshots, we tell the machine that okay, this is my output, and then our network is trained, and we can get the skeleton for the rest of the snapshots, or rest of the structures. So I was mentioning about the little detail about this UNet. So at each level of this contraction branch, we apply some convolution, and then we apply some nonlinear activation. And then we apply some max pooling operation. So basically, resolution is reduced by a factor of 2 in each layer, and the number of images or number of features they are increased in proportion. And then we have a expansion branch where we again apply up convolutions and concatenations. And then what we finally have is this kind of output. So once we get this kind of output, we can easily study the evolution of a superstructure network. So here, for instance, we see for higher Rayleigh number case, Rayleigh number 10 to 6, how superstructure pattern evolves in time. So for instance, you can see that with increasing time, they are separated by roughly 20 time units, let's say, and network readjusts, and you can see that, okay, you have evolution in time. So this is one use of this particular machine learning approach. And then we can immediately compute heat transfer due to this superstructure network. So once we have the superstructure network, like we have pixels corresponding to the ridges which belong to superstructure, we can immediately compute heat transport from those locations. And if we compute the heat transport, and here we show them the fraction of heat transport due to superstructures. So we can see that for Rayleigh number 10 to 5, which is the lowest Rayleigh number for this particular Prandtl number 7, we see that roughly 40% heat is transported due to superstructures. And area occupied by these superstructures is roughly 15% or 12%. If you go to higher Rayleigh number case, the fraction of heat transport decreases due to these superstructures because of higher turbulent, stronger turbulent fluctuations. So turbulent fluctuations contribute more to the heat transport, but area occupied by the network is also decreased. For Rayleigh number 10 to 7, it's decreased even lower value. So we found that with increasing Rayleigh number or increasing thermal driving force, more and more heat is transported due to turbulent fluctuations. But contribution from superstructures is also significant. Okay, so till now we have explored a simple model of convection, which is Rayleigh-Bénard convection, and obviously this is not applicable to the convection in the sun and stellar interiors. So we want to extend our model slowly towards the model, we want to make our model suitable for studying convection in sun. So for the in the first step, we try to introduce some complexity, simple complexity. So if you look at the temperature, variation of temperature, density, and pressure in the convection zone of sun, you can see that they vary by orders of magnitude, and they are highly stratified. For instance, temperature is highly stratified towards the surface. So where if you look at the Rayleigh-Bénard convection, or simple convection model, which is also called Oberbeck-Boussinesq, we call them Oberbeck-Boussinesq model. So convection profile is linear in the conduction regime. But if we somehow allow our thermal diffusivity to vary with temperature, and till now we have assumed it as a constant, and if we vary our thermal diffusivity with temperature as this particular relation, then we can see that even in the conduction state, temperature is stratified, temperature field. So temperature varies slowly, but towards most of the domain, most of the height, but towards the end, it varies very quickly. So what we get in the convection regime, so if we have convection, if we solve our governing equations with this kind of thermal diffusivity, we get this kind of temperature profile. So here I'm showing horizontally averaged temperature field in the vertical direction. So at the bottom plate we have temperature is suppose 1, and at the top plate temperature is 0. So it varies asymmetrically in the vertical direction. Whereas in the Boussinesq model, the temperature varies in symmetrically. So mean temperature or temperature in the bulk, in the midpoint, is the arithmetic mean of the top and bottom plate temperature. But this symmetry is lost in our simple model of convection, which we call as non-Boussinesq model. So this is similar to what is observed in convection, so people study solar convection with inelastic approximations or fully compressible convection. So we have, I already mentioned that we study simple model where we don't consider compressibility of the flow. So in just this simple model, we observe this kind of profile, and it corresponds very well to those observed in compressible convection and in elastic models of convection flows. So we already get some interesting, we start to get some interesting results. And if we look at the velocity field, for instance, here I'm showing the RMS velocity in each horizontal plane as a function of height. So velocity is very small or zeroed at the plates because of the no-slip boundary conditions which we employ, and it increases towards the bulk region. So we see that the velocity profiles are symmetric. So use of this particular thermal diffusivity variation with temperature does not break the symmetry of the velocity field. So why we get this asymmetric profile, and why the temperature field is like why average temperature or temperature in the bulk region is higher than the arithmetic mean. So main reason is that main reason is the functional form of kappa. So this is larger for hotter fluid. So the fluid at the bottom is highly diffusive in our case in this particular model, and due to large diffusivity, it quickly diffuses to like the heat is diffused quickly, and we have very coarse structures compared to the cold structure at the top plate. So the hotter fluid occupies larger part of the domain, larger part of our volume of the flow, and then the mean temperature is also higher. If we look at the temperature structures in our this non-Boussinesq flow, we get this kind of structure. We can see that the mean, so this is a temperature field in the mid plane, and we can see that we have, so mean temperature is, so temperature varies from 0.4 to 1, so which is not symmetric about 0.5, which is the arithmetic mean of the top and bottom plate temperatures. We have higher temperature in the bulk region, and we can also see that the larger, like red structures which are hotter, they are coarser compared to the blue structures, which are colder structures. This is simply because diffusivity is higher for the hotter fluid. So we have coarser structure. So this is a combination of Low-Prandtl-number structures. So we also studied two corresponding cases. So due to varying diffusivity at the top, varying thermal diffusivity, we have different Prandtl and Rayleigh numbers in the entire domain. And this is fixed at the top and bottom plates due to a fixed temperature condition in our simulation. So we have two corresponding Boussinesq cases. So we also simulate those cases to compare our results. And we see that for the simulation corresponding to top Prandtl and Rayleigh numbers, so Prandtl number is 12 and Rayleigh is 10 to 8, and we have very fine thermal structures because of higher Prandtl number and higher Rayleigh number. On the other hand, at the in the Boussinesq convection at lower Prandtl number, we have coarser structures, as we already discussed about this difference. So in NOB case, our structures correspond to these two cases together. Yeah. So what about thermal structures at a different height? Till now, we have focused only in the mid plane. And if we look at the thermal structure at different altitudes, so for instance, this is for OB convection, Boussinesq convection. And here, this is the temperature field in some magnified region of the cross section. And this is how the hot and cold ridges look like. And if you look at the corresponding temperature field at the bottom plate and at the top plate, so this is displayed by vertical temperature gradient. And if you look at this particular quantity, the strongest thermal structures are immediately visible. And we can see that there is very strong correlation between like thermal structures at the plate to the structures in the mid height in the mid plane. So this pattern is correlated strongly throughout the fluid, and we also get similar correlation between the hot between cold ridges and also the cold plumes generated at the top plate. So there is a symmetry with respect to top and bottom plate in the OB convection case, and scales are very highly correlated. And if we now look at the temperature field in the NOB case, non-Boussinesq convection. So here I'm showing you temperature field at different altitudes. For instance, temperature close to the bottom plate, then at 20% height, then 80% height, and 98%. So you can see that I have indicated the wavelength of the pattern or pattern scale by this arrow. So this pattern scale does not change, but we have finer and finer granules on the top of this coarse temperature field or on the skeleton. And this is because the thermal diffusivity decreases towards the top plate, towards the colder region. So finer and finer granules develop on these hotter, like coarse structures. So this symmetry is clearly broken with respect to midplane. We have although the skeleton is same, we have very different structure at the top and bottom plates. So temperature field is completely like it does not show any symmetry in our case in non-Boussinesq convection. We can quantify this asymmetry in the temperature field by studying the thermal variance spectra. So for instance, I compute the Fourier transform of the temperature field in various planes, which I showed in the previous slide. And if you look at the temperature at the power spectrum, at thermal variance as a function of the wave number, you can see that they all peak at the exactly same wave number. So this corresponds that the large scale pattern scale is same at all the wave number. But if you focus at the larger wave numbers, so thermal variance contained in smaller length scale or larger wave numbers, that increases as you approach the top plate. So this is because finer and finer structures or granules develop in the flow. So this is just to show quantitatively that our temperature field becomes more and more finer in structure. And yeah, you can also measure this asymmetry more quantitatively if you sum of the thermal variances in all the wave numbers corresponding to small scales. So if you choose a particular wave number and sum all the thermal variance larger than this scale and divided by the thermal variance in large scales, you get this kind of quantity. And we can see that for the non-Boussinesq case, this thermal variance is asymmetric. It increases, like thermal variance in small scales increases as we go towards top and bottom plate, but this is more towards the top plate. Whereas in Boussinesq cases, this increase is symmetric. Okay, so finally, in our recent effort, we are trying to understand basically, since the convection in sun is very, like it occurs at extreme Prandtl numbers and Rayleigh numbers also. So, but the Prandtl numbers of 10 to minus 6, it's very difficult to achieve in numerical simulations right now. So, and since the flow is very turbulent, so we are interested in knowing what kind of turbulent Prandtl number is there. So basically, as a similar to molecular Prandtl number, we have turbulent Prandtl number if we compute like turbulent viscosity or turbulent diffusivity. So idea is that if you have a turbulent flow, then lots of mixing occurs due to these turbulent fluctuations. And these mixing processes correspond to turbulent viscosity or diffusivity, and by computing the ratio of these two, you can get turbulent Prandtl number. And we want to see what kind of Prandtl number may be there, or turbulent Prandtl number may be there in solar convection case. So we did like right now we are performing 2D convection to achieve very low Prandtl numbers. So you can see that Prandtl number is 10 to minus 4, which is very challenging to achieve in 3D. So that's why we are doing it in 2D right now. And so this is 2D convection. We have a varied Prandtl number from 12 to roughly 10 to minus 4. And we compute these viscosities and diffusivities using K epsilon approach, which is standard approach in engineering models. And so atmospheric models, they use this kind of approach to study, to get the turbulent viscosities. And we follow the same approach and we compute turbulent Prandtl number. And an important result is that we see that turbulent Prandtl number is increasing as we are decreasing the molecular Prandtl number. So it would be very interesting if we can say that effective Prandtl number is higher, very high compared to the molecular Prandtl number. So that will be easier to build a model based on like for the solar convection case if our turbulent Prandtl is not very low. Yeah, so that's it. So to summarize, we have explored thermal convection in extended domains with special emphasis on Low-Prandtl numbers to understand solar convection to flows in solar convection zone. And these extended like convection extended domain is important because the flows in these natural settings are horizontally extended. And our model is still too simple, so we want to extend our models towards by incorporating other complexities, so that our model becomes more realistic and we can get some insight into real solar solar convection flows. So yeah, with this, I'd like to thank all of you for listening to this talk, and yeah, thank you. I'll be happy to answer any questions.
Thank you, Ambrish. That was a great talk.
Thanks.
Yeah, now we are open to questions.
Ambrish, the last graph you showed is for 2D, right?
Yeah, it was 2D.
Okay, thank you.
Yeah, Axel, go ahead.
Thanks for a very interesting talk.
Thank you.
I was interested in the prescription that you used for kappa. Kappa depends on the temperature and the density according to standard radiative diffusion prescriptions. I wonder whether
here
it would. Yes, exactly. So why don't you put a standard prescription for the opacity, in which case you get a dependence on both temperature and density at the same time?
Okay, so normally in solar convection, for instance, this thermal conductivity varies as like T cube in solar convection zone. You also have variation in this in density.
Yes.
But yeah, so since our model is incompressible, we still have incompressible flow. So we just prescribe this effect, like we have turbulent, we have molecular diffusivity, this thermal diffusivity, and we just vary molecular diffusivity. And
so your density is still constant, you say?
Sorry?
Are you saying density is actually still constant?
Density, right. Density is still constant.
I see. Okay, because it says non-NOB model. I thought this was So it was stratified.
So important point is that even though our density is constant, we get lots of like properties of our flow are similar to those properties observed in like inelastic models or fully compressible convection.
Okay, I see.
Yeah, we have discussed this in this paper.
Okay, thank you very much. I will look at the paper.
Thank you.
Any excuse to have Axel look at our paper is a good excuse.
Yes. Absolutely, I should do that.
Anyone else? Raise your hand, use the Q&A feature, chat box, anything. Yes, Srini, do you have any question for him?
No. I've been talking to him endlessly. So.
Okay, then let us stop. Let us thank the speaker. Thanks again, Ambrish.
Okay, thank you.
Talk, and see you all next week. Bye.
Bye-bye.
Okay, thank you, Ambrish. Thank you, Dimitra.
Thank you.